Welcome to Maths with EJD. In this video, I'll be talking about Fourier series and partial differential equations. Generally speaking, we're talking about applications of Fourier series. So I'll be taking this in like three different videos, talking about applications of Fourier series in partial differential equations, in signal processing, and of course in physics. Okay. So this one is about partial differential equations. So let's just go for that. So the first application in partial differential equations that we'll be discussing would be about solving the heat equation. So from the history I talked about concerning Fourier series, right? Joseph Fourier discovered this concept when he was studying heat equation. All right. So the one dimensional, the one dimensional heat equation is given by partial u of x, partial u of x comma t, partial t, which is equal to alpha partial squared u of x comma t, partial x squared. So this is a one-dimensional equation in the sense that it's in space we are talking about just the x dimension, no y and z. So if it's two-dimensional, that'll be xy. If it is three-dimensional, that'll be x, y, z. So here we just have space and time, and that is why it is partial differential equation. Partial differential equation has two dependent variables. Uh, here x and t, x for space and t for time. Okay, so the one-dimensional heat equation is given by this expression. So this actual expression now, uh, using Fourier series, using Fourier series, the solution, here we are looking for u, right? So the solution u of x comma t can be expressed, that's small u actually, for the sake of representation. So u of x comma t can be expressed, can be expressed as u of x comma t equals summation from n equals 1 to infinity of bn e raised by minus lambda n t, then sine n pi x over the length. We are talking about heat flow in a part in a rod of length L, you know. That's the idea. Maybe one of these days when I get to talk about solving partial differential equations, maybe we can get to actually talk about this explicitly. So that can be expressed as u of xt like that, where lambda n are the eigenvalues. They are the eigenvalues of the spatial operator, the spatial operator determined by the boundary conditions. So when we get to that point, I will explain all of these things one after the other. But here I'm just trying to give an overview. So, all right, so that's one application in partial differential equations of Fourier series. Now let's talk about another application that's talking about wave equation, right? So let's talk about applications to the wave equation, to the wave equation. Okay. Now we've talked about its equation. So the wave equation itself, the wave equation for a vibrating string, like when you're playing a guitar, so that's the guitar string as it's vibrating. So the wave generated in it, the wave equation for a vibrating string is this expression, partial squared u of x comma t dt squared equals c squared partial squared u of x comma t dx squared. You have both x and t as dependent variables. So here we can actually solve also. Fourier series, solving with Fourier series, the solution the solution is u of x comma t is equal to summation from n equals 1 to infinity of an sine of n pi x over L cos c omega n t, something like this, where omega n are the natural frequencies determined by the boundary conditions. Determined by the boundary conditions. All right, the third application, as far as partial differential equations is concerned, the third application is Laplace equations applications to Laplace's equations. Laplace's equation. Okay, so here the Laplace's equation in steady state problems, is given by this thing. I think it's called nabla. So like a triangle facing up. So that's like nabla squared of phi x y z equals 0. So in cylindrical coordinates, cylindrical coordinates, the solution can be expressed as phi of r theta z equals summation from n equals 1 to infinity an sine n pi r over big R e I n theta. So very soon we're going to see some other expressions of these things. So this expansion helps solve problems related to electrostatics, fluid flow, and heat conduction, all these things, and heat conduction. Okay. So these are some applications of Fourier series in partial differential equations. So I mean, we didn't actually go embark on solving the equations properly, actually, but maybe when I talk about solving differential equations, I can actually get to discuss that. So I'll be talking about signal processing in the next video. So subscribe to this channel, hit the notification bell so you can always get alerted each time a new video is released. Don't forget to comment. Let me know how helpful these videos are for you. Also, let me know if there's a problem you'd like me to solve or a topic you'd like me to teach. Also, like and share so that more people can have access to this great channel. Till I come your way again, keep doing maths right. Bye.